Intermediate metal conduit, or IMC, used as a raceway for a submersible pump must be properly bonded to the equipment grounding conductor, or EG, according to the National Electrical Code. This is crucial for safety and to comply with electrical regulations. The primary goal of bonding is to create a low impedance path for fault current, ensuring that overcurrent protection devices, such as circuit breakers or fuses, operate quickly to clear faults. When a fault occurs, such as a short circuit between a live conductor and the metal conduit, the fault current flows through the conduit back to the source. A properly bonded conduit system provides a reliable path for this current, enabling the overcurrent device to trip and to energize the circuit, preventing electrical shock hazards and minimizing damage. Several sections of the National Electrical Code address the requirements for bonding metal raceways, including IMC. One key section is National Electrical Code Article 501.16a, which states that exposed metal raceways shall be connected to the equipment grounding conductor where accessible. This provision ensures that any accessible portion of the metal raceway is effectively grounded, reducing the risk of electrical shock. Another relevant section is National Electrical Code Article 501.16b, which specifies the requirements for connecting electrical metallic tubing (EMT), intermediate metal conduit (IMC), and rigid metal conduit (RMC). It mandates that these raceways shall be connected every 10 feet, or 3.5 meters. This requirement ensures continuous grounding throughout the raceway system, providing a reliable path for fault current. Furthermore, National Electrical Code Article 502.35 addresses the specific case of metal raceways supplying equipment located outdoors. It states that a metal raceway supplying equipment located outdoors, including metal raceways used as service entrance conductors, shall be connected to the equipment grounding conductor using a bonding jumper. This provision is particularly relevant for submersible pumps, as they are typically installed outdoors and require a robust grounding system. In the specific scenario of a submersible pump installation, the IMC raceway running from the subpanel to the pump must be bonded to the equipment grounding conductor at both ends and at any intermediate point as required by the code. This is typically achieved using a metal bushing with a lock nut or grounding bushing. A metal bushing is a fitting that is installed on the end of the conduit, providing a smooth surface for the conductors to pass through and protecting them from abrasion. A lock nut is used to secure the bushing to the conduit. A grounding bushing is a specialized type of bushing that includes a provision for connecting a grounding conductor. When installing a grounding bushing, the equipment grounding conductor is connected to the bushing using a screw or other suitable connector. This establishes a direct connection between the conduit and the grounding system. The proper installation of grounding bushings is critical for ensuring effective bonding. The bushing must be securely attached to the conduit, and the grounding conductor must be properly connected to the bushing. It is also important to ensure that the grounding conductor is properly sized to handle the anticipated fault current. The size of the grounding conductor is determined by the size of the circuit conductors, as specified in the National Electrical Code Table 250.122. In addition to using grounding bushings, other methods can be used to bond the IMC to the equipment grounding conductor. One common method is to use a bonding jumper. A bonding jumper is a short length of conductor that is used to connect two metal parts together. In the case of an IMC raceway, a bonding jumper can be used to connect the conduit to a grounding electrode, such as a ground rod or a metal water pipe. The bonding jumper must be sized according to the National Electrical Code Table 250.102, and it must be installed in a manner that provides a reliable electrical connection. Another method is to use a listed fitting that is specifically designed for bonding metal raceways. These fittings typically include a screw or other mechanism for connecting the grounding conductor to the fitting. When using a listed fitting, it is important to follow the manufacturer's instructions for installation. Improper installation can compromise the effectiveness of the bonding system. It's also critical to verify the integrity of the grounding system. This can be done by performing a ground impedance test. A ground impedance test measures the resistance of the grounding path from the equipment back to the source. A low resistance value indicates a good grounding connection, while a high resistance value indicates a potential problem. Regular inspections and maintenance of the grounding system are also important. This includes checking for loose connections, corrosion, and other signs of damage. Any problems that are identified should be corrected promptly to ensure the continued effectiveness of the grounding system. In summary, the National Electrical Code requires that intermediate metal conduit (IMC) used as a raceway for a submersible pump be properly bonded to the equipment grounding conductor (EC). This is essential for safety and to comply with electrical regulations. The bonding can be achieved using a metal bushing with a lock nut or a grounding bushing, as well as other methods such as bonding jumpers and listed fittings. Proper installation and maintenance of the grounding system are critical for ensuring its effectiveness. By following these guidelines, you can ensure that your submersible pump installation is safe and code compliant. Remember to always consult the latest edition of the National Electrical Code and local electrical codes for specific requirements in your area. If you are unsure about any aspect of the installation, it is always best to consult with a qualified electrician. Furthermore, it's important to note that the requirements for bonding metal raceways can vary depending on the specific application and location. For example, in hazardous locations, such as those containing flammable gases or vapors, more stringent bonding requirements may apply. These requirements are outlined in Article 500 of the National Electrical Code. In addition, local electrical codes may have additional requirements that are not covered in the National Electrical Code. It is therefore essential to consult with the local electrical inspector to ensure that your installation complies with all applicable codes and regulations. The equipment grounding conductor plays a vital role in the overall safety of the electrical system. It provides a low impedance path for fault current, which helps to quickly trip over current protection devices and prevent electrical shock hazards. The equipment grounding conductor is typically a green or bare copper wire that is run along with the circuit conductors. It is connected to the metal enclosures of electrical equipment such as motors, transformers, and panels. The equipment grounding conductor is also connected to the grounding electrode system, which consists of grounding electrodes such as ground rods, metal water pipes, and concrete encased electrodes. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for lightning currents. When a fault occurs, a fault current flows through the equipment grounding conductor back to the source. This causes the voltage on the equipment enclosure to rise. If the equipment enclosure is not properly grounded, the voltage can rise to a dangerous level, which can result in electrical shock if someone touches the enclosure. However, if the equipment enclosure is properly grounded, the voltage will be limited to a safe level. The equipment grounding conductor also helps to reduce electromagnetic interference, or EMI. EMI is unwanted electrical noise that can interfere with the operation of electronic equipment. By providing a lower impedance path for fault current, the equipment grounding conductor helps to reduce the amount of EMI that is radiated from electrical equipment. In addition to the equipment grounding conductor, another important component of the grounding system is the bonding jumper. A bonding jumper is a short length of conductor that is used to connect two metal parts together. Bonding jumpers are used to ensure that all metal parts of the electrical system are at the same electrical potential. This helps to prevent electrical shock hazards and reduce the risk of fire. Bonding jumpers are typically installed between metal raceways, metal enclosures, and other metal parts of the electrical system. The size of the bonding jumper is determined by the size of the circuit conductors, as specified in the National Electrical Code Table 250.102. It is important to ensure that the bonding jumpers are properly installed and securely connected. Loose or corroded bonding jumpers can compromise the effectiveness of the grounding system. The National Electrical Code provides detailed requirements for the installation of grounding and bonding systems. It is essential to follow these requirements carefully to ensure the safety and reliability of the electrical system. Improperly installed grounding and bonding systems can result in electrical shock hazards, fires, and equipment damage. In addition to the National Electrical Code, local electrical codes may have additional requirements for grounding and bonding systems. It is therefore important to consult with the local electrical inspector to ensure that your installation complies with all applicable codes and regulations. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the requirements of the National Electrical Code and local electrical codes, you can help to ensure that your electrical system is properly grounded and bonded. This will help to protect people from electrical shock hazards, reduce the risk of fire, and prevent equipment damage. Remember, working with electricity can be dangerous. If you are not qualified to work on electrical systems, it is always best to consult with a qualified electrician. They have the knowledge and experience to perform the work safely and correctly. In addition to the technical aspects of grounding and bonding, it is also important to consider the practical aspects of the installation. This includes choosing the right materials, using the right tools, and following proper installation procedures. When choosing materials for grounding and bonding systems, it is important to select materials that are compatible with the environment. For example, in corrosive environments, it is important to use corrosion-resistant materials. It is also important to select materials that are listed and labeled by a recognized testing laboratory. This ensures that the materials have been tested and found to be safe and reliable. When using tools for grounding and bonding systems, it is important to use the right tools for the job. This includes using the right size of wrench, screwdriver, and crimping tool. It is also important to use tools that are in good condition and properly maintained. When following installation procedures, it is important to follow the manufacturer's instructions carefully. This includes following the torque specifications for all connections. It is also important to inspect all connections to ensure that they are tight and secure. By paying attention to the practical aspects of the installation, you can help to ensure that the grounding and bonding system is installed correctly and will provide years of reliable service. Finally, it is important to remember that grounding and bonding are not a one-time task. The grounding and bonding system should be inspected regularly to ensure that it is still in good condition. Any problems that are identified should be corrected promptly. Regular inspection and maintenance will help to ensure that the grounding and bonding system continues to provide the necessary protection. To reiterate, the use of intermediate metal conduit, or IMC, requires adherence to specific bonding practices. The National Electrical Code, in sections such as 501.16a, 501.16b, and 502.35a, mandates the proper connection of metal raceways to the equipment grounding conductor, or EG, particularly in outdoor applications and within certain hazardous locations. The primary purpose of bonding is to create a low impedance path that facilitates the safe flow of fault current back to the source, enabling overcurrent protection devices to operate effectively. This process safeguards against electrical shock and minimizes potential damage. Methods for achieving this bonding include employing metal bushings with lock nuts, grounding bushings, bonding jumpers, and listed fittings designed for this specific purpose. Each of these methods ensures a secure and reliable connection between the IMC and the EGC. Proper installation is crucial, including verifying the tightness of connections and the correct sizing of conductors, as specified in tables 250.122 and 250.102 of the National Electrical Code. Regular inspections are also essential to maintain the integrity of the grounding system, checking for corrosion, loose connections, and other forms of damage. When working with electrical systems, safety is paramount. It's recommended that you consult with a qualified electrician if you're uncertain about any aspect of the installation or maintenance process. They possess the expertise to ensure the work is completed safely and in compliance with all relevant codes and regulations. Remember to always reference the most recent edition of the National Electrical Code and any local electrical codes that may apply to your specific location. These codes offer comprehensive guidelines for grounding and bonding, ensuring the protection of both personnel and equipment. Also, always ensure you disconnect power to the circuit before working on any electrical components. This will help prevent accidental electrical shock. Double check that the power is off using a voltage tester before beginning work. Always use appropriate personal protective equipment, or PPE, when working with electricity. This includes safety glasses, gloves, and insulated tools. Never work alone on electrical systems. Always have someone nearby who can assist you in case of an emergency. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician to do the work for you. They have the training and experience to perform the work safely and correctly. Finally, remember that electrical systems can be dangerous if they are not properly installed and maintained. By following the safety guidelines outlined above, you can help to protect yourself and others from electrical hazards. Submersible pumps are often used in wet or damp locations, so it is important to ensure that the grounding system is properly installed to protect against electrical shock. In addition to grounding the metal conduit, it is also important to ground the pump motor itself. This can be done by connecting the equipment grounding conductor to the motor frame. The grounding conductor should be sized according to the National Electrical Code Table 430.250. When installing a submersible pump, it is important to follow the manufacturer's instructions carefully. This includes following the torque specifications for all connections. It is also important to inspect all connections to ensure that they are tight and secure. By following these guidelines, you can help to ensure that your submersible pump is installed safely and will provide years of reliable service. Always check local regulations and codes. The NEC is a guideline, but your local municipality may have stricter guidelines that you must follow. This could include additional inspections or required permits for the work. Ignoring these rules could result in fines or having to redo the work. It is always best to check beforehand to ensure that you are in compliance. Keep records of all work done. This includes dates, materials used, and any inspections that were performed. This documentation can be helpful in the future if there are any issues with the electrical system. It is also a good idea to take pictures of the installation before and after the work is completed. These pictures can be helpful in the future if you need to troubleshoot any problems. Ensure proper labeling. Clearly label all electrical panels and circuits. This will help to prevent confusion in the future and make it easier to troubleshoot any problems. Use a permanent marker to label the circuits and panels. Do not use tape or stickers, as these can fall off over time. Keep the work area clean. A clean work area is a safe work area. Remove any debris from the work area before you start working. This will help to prevent accidents. After you are finished working, clean up the work area and dispose of any waste materials properly. Ensure proper wire management. Proper wire management is essential for a safe and reliable electrical system. Use cable ties to bundle the wires together and keep them organized. Do not allow the wires to hang loose or become tangled. Use wire staples to secure the wires to the wall or ceiling. Make sure that the wires are not pinched or damaged. Use junction boxes to make splices and connections. Do not make splices or connections outside of junction boxes. Use wire connectors that are properly sized for the wires that you are using. Make sure that the wire connectors are properly tightened. By following these wire management tips, you can help to ensure that your electrical system is safe and reliable. Also, use correctly sized breakers and fuses. Using oversized breakers or fuses can be extremely dangerous. These devices are designed to trip and cut off power when there is a fault, like a short circuit, which can cause a fire. If the breaker or fuse is too large for the circuit, it will not trip when there is a fault, and the wires can overheat and start a fire. Refer to the NEC or consult with a qualified electrician to determine the correct size of breaker or fuse for your circuit. Use GFCI outlets in wet locations. GFCI outlets, or ground fault circuit interrupter, are designed to protect people from electrical shock. They work by monitoring the current flowing through the circuit. If the current flowing out of the outlet is different from the current flowing back in, the GFCI outlet will trip and cut off power to the circuit. GFCI outlets are required in wet locations, such as bathrooms, kitchens, and outdoor areas. They can also be used in other locations where there is a risk of electrical shock. Test GFCI outlets regularly to ensure that they are working properly. Press the test button on the outlet. The outlet should trip and cut off power to the circuit. If the outlet does not trip, it should be replaced. When testing GFCI outlets, you can use the GFCI tester or the built-in test button on the outlet. When replacing an outlet, be sure to turn off the power to the circuit at the breaker box. Use a voltage tester to confirm that the power is off before you begin working. Follow the manufacturer's instructions carefully when installing the new outlet.